Okay, section 5 of particle physics, and I'm going to change what I did in my standard model because we're starting to get into the interesting stuff. So I've got rid of protons and neutrons because actually those are not particles. They are not what we call fundamental particles. They're actually made of something else. So does that matter in normal life? No, it doesn't. Does it affect chemistry? No, it doesn't. But in terms of knowing the structure and how radioactivity changes the energy within atoms, that we need to go much deeper in. Okay, so we're going to look at this group here now, which feature in the group called hadrons, but what these are things called quarks. So we're going to look at quarks, or quarks if you prefer, as a way of finding out what they are. And again, we have the most stable ones, slightly less stable, and then least stable. Okay, and at A level, we'll really just look at these three, okay, the up, the down, and the strange. The others, truth and beauty, as they originally called, but they tend to now be a bit more boringly called top, bottom, and charm, those are all behaving in a similar way, but we don't study them because that just expands the probabilities out hugely. So we're going to look at the main kind of principles as such. Okay, very short little piece today in terms of notes, and really straightforward, but getting you to start thinking about the ideas. So what they are actually tiny subatomic particles that appear within the subatomic particles that we are used to. So we will find these in the nucleus, and just like as I said here, Rutherford firing particles at a larger structure, gold leaf, and discovering the nucleus in the middle, we're effectively scaling this down. So instead of the atom, this is now a nucleon, a particle in the nucleus, and again we're using electron scattering and other things to find out what goes on. We can use light, but it has to be incredibly high energy, so it's much easier to get high energy by smashing particles together, or more correctly, getting them to diffract around like waves and giving us a diffraction pattern. Okay, so we can think of it in two ways. Now these are high energy, that's why we don't notice them. So these are moving around incredibly quickly. However, if we fire particles in at approaching the speed of light, 50% of the speed of light, 90% of the speed of light, then what happens is these effectively are frozen into a fairly flat pancake-like structure, a TD structure like that. So if your particles are coming directly towards it, it flattens, and so you get a very definite pattern from which you can find using your diffraction pattern beyond it. Okay, so that's the kind of the basis beyond it, and really, it's getting within living memory now for a lot of people. 1968 is when this research was used, and by using that, they found the structure of these simple things, and it changed people's minds so much. It even featured in rock songs and so on. So there is a song called Quarks, for example. Anyway, what are quarks? We know that they exist inside protons and neutrons. What actually are they is a bit of a harder question. We know that there are 6 types, and again, like all particles, they have their own antiparticle as well. So that actually makes 12 types. Okay, and the combinations of them, the combinations of their properties, gives us the property of the particle. So this, for example, is an image of a proton. I can tell why, because the properties of the up and down quarks within it make up protons and neutrons. Okay, so most of our questions we'll be doing will be based upon up and down quarks, but there are strange quarks as well. These are the least massive, so they need the least energy to make them. Okay, E equals mc squared. The third least massive is the strange. Charm is quite a lot more massive, so it's harder to make, and then these are way more massive. Okay, so it takes a lot of energy to create this top level, and when we get into leptons, there's an equivalent kind of structure. Okay, or idea rather. So we have them. We're going to just concentrate on these three, and we do have some of their properties here, but I'm going to introduce you to some more. If you go onto the AQA book, they've got a table with various properties. We're going to mainly concentrate on charge, okay, Q, because actually that's the most important one that we're going to use. However, as I've said here, they also consider strangeness. So I'm going to bring that idea in. Okay, now strangeness is a type of charge. That's the way of thinking about it. So think of this as charge, not an electric charge, which is our normal everyday version here, okay, but a different type of charge, which again adds up or cancels out. Okay, so it works in exactly the same way. Proton, positive charge equal negative charge, put them together, they add up to nothing. So from your data books you can find these. An up quark is going to be plus 2/3. Okay, and that's probably the one to remember the most. 2/3 of the fundamental charge. Okay, the charge units that is on our data sheet, 1.6 times 10 to the minus 19. So actually it's a fraction of that common charge value. And all of these are. Now, the others basically have the same property in terms of charge. They're both minus 1/3. Okay. Now what that means is that when we put them together, we need to add up their charges to find out what's going on. So over here, for example, we've got 2 ups and a down. That means I'm going to have 2/3, 4/3 positive, minus 1/3 will equal 3/3, or 1 plus 1.6 times 10 to the minus 19, which is the charge of an electron, proton, which does work. Okay, but we would need 3 of them to make it work. If I added those two together, I'd end up with 1/3 of an electron charge, and that cannot exist. All particles, as we shall find out, baryons, mesons, and hadrons, all have 3 particles within them. Okay, sorry, all have quarks within them. So some have 2, some have 3. We'll come back to that in a bit. But the main group is the ones that we experience every day. These are baryons. So I'm not going to explain that at the moment, but protons and neutrons are the only baryons you need to know about. So they have 3 quarks inside. There are other baryons which have 3 quarks inside, but that isn't important for what we are. So in terms of checking the mass, what we need to think about is actually, we'll give them a number. So just like charge has to add up, our baryon number has to add up. Okay, and they're nice and straightforward in that they're all 1/3. Now, the interesting bit is this strangeness. The standard level of strangeness is a minus charge, a bit like electrons, because it's based on that same idea. So strange quarks have a strange charge. How does that come about? Well, it's because they always, whenever you smash particles together, you get all kinds of different particles being created in what appeared to be quite a random manner. But when you involved a certain type of property, they always got made in the same way, and that was strange. And the name kind of stuck with it. They're the only particles that are strange out of all 6 of them. The other ones that we're not going to cover, like top, has a top charge, which is unique to the top quark. Charm, bottom, those are all electrical charges. Those are all charges as well, like electric charge. Doesn't matter for what we want to know, but a curious little thing. Now, if we go to the anti-down, anti-up, and anti-strange, they are just the opposite of each other. So minus 2/3 in the middle, and plus 1/3. Okay, so they have the opposite charge, as we said, but they also have every other quantum number, every other quantum property, like electric charge, which is a quantum property, all of these are the opposite as well. So this is minus a third, minus a third, minus a third, 0, 0, and plus 1. Okay. Now, why don't we see these? Because the energy they need to make them or binding them together is incredibly huge. This there is where we talked about our nuclear strong force between neutrons and protons. Well, there's a similar thing inside called gluons. So this gluon force keeps them glued together. It's incredibly strong. So if we were to try to remove them from each other, what would happen is if there's so much energy released, E equals mc squared means that there'd be enough energy to actually create another pair of matching quarks. So quarks can actually, seemingly like microbes, double in number. Okay, why? It's all about the crashing and collisions and so on that we do that can rip them apart. If it does rip them apart, as I say, it's enough to create another pair. So interesting, but there we go. How does that factor what we do? Well, if we know what the quarks are, and this is like our idea of electrons in chemistry, if we know where these have gone, except we can create more, if we know where they are and we check they add up, then we can tell if a reaction can happen or not. Okay, so this is a nuclear reaction, can happen or not. So to do that, we need to kind of think about how we group things, and it all depends on how many quarks they've got, or whether they have quarks. Can not all particles do. Okay, so if we think of these as building blocks, okay, as far as we know, practically, as far as we know, these are the smallest things that exist. Okay, theoretically, perhaps there's other things. Whether we'll actually find them, don't know. So what we have is they'll split into groups that have quarks and groups that do not. Simple as that. And this is where our other chapters come in, really. But what is it to do with? Well, it's these Greek words. So the two main groups are hadrons, as in the Large Hadron Collider, and that is basically Latin for heavy. It is everything made from quarks. Whereas leptons, light, are fundamental. Okay, so these are not fundamental, they're made of smaller particles. These are fundamental, we don't think there's anything inside them. Okay, so an electron is a lepton, comes in that group. Okay, how do we find it all out? How do we know all this stuff? Is by looking at hundreds and hundreds and hundreds of thousands of reactions. Sorry, I'm understating it. Millions and millions and millions and millions and millions of reactions. Okay, millions every second are being created in places like CERN. So just like studying chemical effects in the 18th century and 19th century to make chemistry, this is how we got these kind of patterns and started grouping and so on. So that produced us this almost periodic table of stuff. So we're going to concentrate, or we have just concentrated on this corner here, but if we start thinking about the other particles as well and the other types of charge that they may have, then you can start to see how complicated it's got to be if you've got to check that the electric charge adds up, the baryon number adds up, the strangeness adds up, the chrominess adds up, the bottomness adds up, the topness adds up, and you've always got to get 3 in the same particles. It could be 3 downs, it could be 2 downs and an anti-down, it could be a down and a top and a bottom. You know, the combination numbers are huge. So the phrase that's often said when they originally started was the particle zoo, because there just seems so many different particles. But searching through all these collisions and decays as they fall apart over time looks at and has given us this idea of 6 different particles. And that gives us that combination there. Okay, our 6 quarks. So our hadron group are the ones with quarks in. Those that don't have quarks in are our lepton groups. And that is what everything is made from. Okay, all matter that we know of, all dark matter, etc., has to fit in with what we know so far. If it doesn't, we'd have to rewrite everything. And that's why the understanding of dark energy is problematic, to say the least. Dark matter, yeah, we can fit that in with this, no problem. We can create dark matter and so on within the lab as well, or particle accelerators. But can we make the other stuff? Dark energy, we're not really sure. So we're still struggling with this. As I said, Higgs was only discovered or shown to exist within the last 10 years. Okay, so it's a rapidly changing area.